let's have a go at adding, let's scale up the problem from not just adding 2 1-bit signals, let's add 3 1-bit signals. So we've got 3 signals, and let's say they have place value 1. How do we build a circuit which adds these up? Well, straightforwardly, we pick any 2 of them and add them. We know how to add 2 1-bit signals, so we can use that. So let's add these 2 together with a half adder. And what comes out is the total of those 2 with some place values. What place value label should I put on this wire? 1. And what about this wire? 2. So we put in 2 ones columns, and out come a ones column and a twos column. Okay? So the rule is, remember, a number has 1 digit at each place value. So when you've only got 1 signal left at each place value, that means you've finished. And if you've got more than 1 signal at a given place value, you know how to add them. So you can just keep adding stuff until you're finished. That's how it works. Just add stuff until you're finished. You don't have to remember a particular system. You don't have to remember a particular diagram. You just have to remember to add stuff with the same place value until there's nothing left to add. Until you've got 1 signal at each place value. That's all there is to it. So here you can see we've still got 2 signals of place value 1. So we better add them all. So what place value should I put on the outputs? 1 here, 2 there. And that tells us, because we've only got 1 signal left at place value 1, that we have computed the ones of the answer. Woohoo! However, we still have 2 signals at place value 2. So, what are we going to do? Add them! Writing that very small in the corner for a reason. Out come 2 signals. What are their place values? The one on the right? 1. Careful. 2. If the signals coming in were worth 2, the signal on the right coming out will be worth 2, and the signal on the left will be worth 4. So on the right you get the same place value that came in, and on the left you get twice that. Alright?
But wouldn't that go on infinitely then?
Yes. And that's just as well, because we want to be able to add large numbers, right? The numbers keep getting bigger, but that's fine. The method still works the same.
Why is that hat small?
That hat is small because we're going to take a look inside this box in just a moment. So one thing we didn't do for this one, this thing is called a full adder, which I call FAD, like a diet. And sorry, I have to keep telling dad jokes in case I have an accident with my contraception. So we're adding three signals with place value 1, so what's the largest total we can possibly get out? Hang on. 3. Each of them has place value 1. So a 1 in each of these inputs is only worth 1. It's not like a binary number, a 3-bit. These are 3 1-bit numbers, not 1 3-bit number. That's what the place values are telling you, is that these are 3 1-bit numbers. So a 1 in each of these means just 1. And so the largest possible total we can get is 3. So how many bits? So will we ever actually make it into the 4s column? there's no way this total is ever going to be 4 or more. It's going to be 0, 1, 2, or 3. So we don't actually need this column. So I'm going to sew it off. But keep the other 2. And then I can simplify my circuit by looking at what's inside this had box, which is why I left myself plenty of room. There's an XOR here, wired up to both inputs. And there's an AND here, which is not being used. So you could actually cheerfully just dispose of that extra bit of circuitry and make the whole thing with 2 half adders and an XOR. So this is the usual way to make a full adder. It's 2 half adders and an XOR, but you should remember that that's only because we knew there couldn't possibly be a carry into the 4's column. Okay? If we write out the truth table for this, we've got 3 inputs, X, Y, and Z. We're still going to get 2's and 1's coming out. Somebody really should make a set of CS106 rubber stamps for just writing out the left-hand side of a truth table. It would save so much time in exams. And let's just make sure that we can add. We know we don't need to spend our time figuring out exactly how to feed these numbers through the circuit to see what comes out. Because we know because of the way we built it that it's doing adding. So let's just summarize. 0 plus 0 plus 0 is going to be what? 0, which will be 0, 0 in 2 bits of binary. 0 plus 0 plus 1 is?
1.
0 plus 1 plus 0?
1.
0 plus 1 plus 1?
2.
1 plus 0 plus 0? 1 plus 0 plus 1? 1 plus 1 plus 0? And 1 and 1 and 1 is?
3.
Got to be good looking because you're so hard to see. You're all too young. Okay. So that's a full adder. That allows us to add 3 signals with the same place value. So again, it's not in general just 1s and 2s. It's 2 to the n, 2 to the n, 2 to the n, 2 to the n, I better zoom out, and 2 to the n plus 1. So when you happen to have 3 signals with the same place value, you can add them with a full adder instead of a half adder, and that happens all the time.